It's a plane! It's a bird! It's a bug! No, definitely a plane. Every day, millions of airplanes, boats, bugs, and birds utilize systems of fluids to transport themselves. What are the main things that they all have in common? Lift! However, they also have imperfections in their surfaces that cause drag and less than perfect laminar flow. In the realm of planes, these imperfections due to the particles on the wings are very costly. The ultimate goal of aircrafts are to transport materials using the least amount of fuel possible, and according to NASA, this is achieved by uninterrupted flow, creating streamlines over the wings. Laminar flow is a type of flow in which the fluid travels smoothly and in streamlines, as shown here. In order to look at how planes work, let's look at Bernoulli's principle to see how lift is produced on an airplane wing. Bernoulli's principle states that the pressure of a fluid decreases at points where the speed of the flow increases. So as the plane takes off, the velocity provided by the airplane engines create an airflow around the plane. This principle is utilized in an airplane wing where the design of the wing causes the airflow along the bottom of the surface to be less fast than the velocity along the top, causing a difference in pressure where the pressure decreases above and increases below, creating a lift in the y direction because everything wants to move from high pressure to low pressure. This lift opposes the weight of the airplane, and this is how airplanes are able to fly. However, this only occurs when there is a smooth flow of air over the wing, so this could not occur if the airplane was stationary. If the flow is interrupted, say by a bug hitting the wing and sticking to it, this could cause a loss of lift and a high degree of drag, which we will talk about next. However, we can't forget the x-axis. Along this axis, the relationship between the thrust and drag influence the amount of fuel used. Planes are designed to have the perfect amount of thrust to counteract the drag put on the airplane by the fluid air surrounding it. Drag is the mechanical force generated when a solid body comes in contact with a fluid. If there is turbulent flow over the wing, as seen here, it results in a loss of lift and a high degree of drag. This decrease in flow also causes a decrease in fuel economy, as the engines have to overcompensate to overcome this extra drag, and by doing this, use more fuel. All of these different types of flow and drag are quantified by equations that are commonplace when designing anything that moves through a fluid. Enter Reynolds number. Reynolds number is a dimensionless ratio between an inertial force, which is the resistance to change, and a viscous force, which shows how much force the fluid has. It depends on the length, density, and velocity of the fluid, and the inverse of the bulk velocity, or how sticky the air is. Bringing it back to planes, the Reynolds number associated with the airflow over the wing describes what type of airflow is flowing on the wings. There are three types of forces that are described: laminar, transitional, and turbulent. Laminar is associated with a low Reynolds number, and turbulent is associated with a higher Reynolds number. Transitional is somewhere in between. Though laminar flow is the goal when designing an aircraft, any interruptions in this flow may cause transitional or turbulent flow due to an increase in flow velocity, causing a higher Reynolds number, and this also causes a higher amount of drag, because Reynolds number directly affects the coefficient of drag. Since a low Reynolds number denotes laminar flow, an increase in velocity due to excess material such as bug splatter will bring about a decrease in lift and an increase in drag, causing an increase in cost. However, when the holy grail of laminar flow happens on the wing, it can save around 5 to 6% in fuel usage. When you take into account how many planes fly every day, the fuel savings could be huge. NASA is trying to find a solution to the non-laminar flow problem, and the most promising solution is to coat the wings with a certain type of coating, so when the bug comes along, splat, it doesn't stick around to ride the airplane. While the early data from one of these tests only showed a 40% reduction in bug counts and residue on the wings, that still means that there could be a hefty 2 to 3% saving in fuel. For more information about NASA's upcoming ways to save fuel, visit their website at nasa.gov. Thanks for listening.